Welcome to this Reigate College Maths, Further Maths Core Pure video on complex numbers. This one is on nth roots and also the application of that idea to solving geometric problems. So just switching to what's under the visualizer from the course workbook. So if we think about the equation z to the power of n is equal to 1, that equation, where z is a complex number, that equation has n solutions. So there are n roots to that equation, and they come in this form. They come in the form e to the power of 2 pi I times k divided by n. So n is this number here, and k is the number going from 1, 2, 3 up to n. So it's any of those values. So this gives us our n solutions. So if we just think about what happens when k is equal to n, we're going to get e to the 2 pi I times n over n. So that's e to the 2 pi I, which is just 1. Because if you think about the argument of a complex number which has 2 pi, well, it's going to be on the positive side of the real axis. Here the modulus of this is 1. So this is just 1. If you think about where k is equal to 1, if we raise that to the nth power, we're going to have e to the 2 pi I times 1 over n, all to the power of n. Well, that's going to be e to the 2 pi I times 1. When we raise it to the power, we do just get 1. So what's going to happen is that these nth roots of 1, or nth roots of unity, is the more old-fashioned way of saying that, are spread out around the origin on the Argand diagram at regular intervals, with the angle between them being 2 pi times 2 pi over n. We'll see that in a moment. We can also use this to solve the equations like z to the power of n equals w, and we'll see how to do that in a minute. So let's go to example 1 here. It says solve the equation z to the power of 6 is equal to 1. In other words, we're going to find the 6th roots of 1. So we can use what we've seen here to write down these 6th roots straight away in exponential form. So the roots are going to be well, first of all, 1. We know that 1 is a root of z to the power of n equals 1 for whatever n is. So 1. Then we're going to make n equal to 6. We're going to make k equal to 1, 2, 3, and so on. So we're going to have e to the 2 pi I over 6. We're going to have e to the 2 pi times 2 over 6. So that's 4 pi I over 6, and so on up to e to the, we need n equals 5. So that'll be 10 pi I over 6. This one here comes from k equal to 6. So e to the 2 pi I times 6 over 6. I've put it this end rather than this end. So another way to think of this is k going from 0 up to n minus 1. So these are 1 e to the pi over 3 I e to the 2 pi over 3 I e to the 3 pi over 3i, so that's going to be e to the I, and so on up to e to the 5 over 3 pi I. Sorry, I should have put pi in there. There we are. So let's write each one out and give it in a plus bi form. So Z1 is equal to 1, Z2 is equal to, so we're going to make that this one. Well, it's cos of pi over 3 plus I sine of pi over 3, which is, well, cos of pi over 3 is a half, so it's a half plus root 3 over 2i. Z2, that's this one, is cos of 2 pi over 3 plus I sine of 2 pi over 3, which is minus a half plus root 3 over 2i. That's Z3. Z4 is minus 1. Z5 is, well, it's actually just the conjugate of both of these. So conjugate of this one first, so that's minus a half minus root 3 over 2i, and Z6 is a half minus root 3 over 2i. And then we're asked to sketch these on an Argand diagram. So I'm going to do that here. We're going to draw our imaginary and real axes. There we go. Real, imaginary. Right. And then on here, we're going to put the roots. So my first root is going to be 1. Let's put also minus 1 in. And then we're going to go round an argument of pi over 3. So that's in degrees, that would be 60 degrees. So let's just sketch in a little guideline to help us here. And another one there. I'm sure I've drawn that particularly accurately, but that'll do. And then it needs to be the same distance away. Let's just check. T2. So there, round about there, and around about there. So this would be Z1, Z2, Z3, this is Z4, Z5, and Z6. Just checking to see that I had written down Z6 there. So let's show you that. Sorry, I've got it off the camera. There are 6 sixth roots of 1, and you can see that they all lie on a circle radius 1 around the origin, as we would expect. Let's go on to the next page and have a look at now using this to solve an equation. So we're going to solve the equation z cubed is equal to 4 root 3 plus 4i, giving our answers in exponential form, and we want argument of z, as usual, to be between minus pi and pi. So let's just quickly sketch out a little diagram here. So here's my Argand diagram, and I'm going to put not z on it, but z cubed. So it's 4 root 3 plus 4i. So let's put that in there. 4 root 3 plus 4i. So it's going to be somewhere like that. That's 4i. This is the imaginary axis. This is the real axis. And there is our z cubed. Now, what we're going to do is we're going to work out the modulus of z cubed. So modulus of z cubed is equal to, well, we need to find 4 root 3 squared plus 4 squared, and then take the square root of it. Well, 4 root 3 squared is just going to be 3 times 4 squared, then plus 1 times 4 squared. So we're going to have 4 times 4 squared, which is, actually, let's write it out. 4 root 3 squared plus 4 squared, which is 3 times 4 squared. 4 squared is 16, so that's 48 plus 16. Square root 48 plus 16, which is root 64, which is 8. Now, if the modulus of z cubed is 8, then the modulus of z must be the cube root of 8, which is 2. So modulus of z, and this is true of any of the 3 roots of this equation, is going to be 2. Say so. We can also look at the argument of z cubed. Arg of z cubed is equal to, well, if we consider the angle here, it's going to be tan the minus 1 of, this is going to be opposite here over adjacent, O over A, so 4 over 4 root 3 over 4 root 3. In other words, tan to the minus 1 of 1 over root 3, which is pi over 6 radians. So one of our solutions is going to be, or well, let's write out z cubed. So we can say, so z cubed is equal to 8e to the pi over 6 I. So then one of our solutions is going to be z1 is equal to 2 e to the, we want to divide that argument pi over 6 into 3, so pi over 18 I. Then z2 is going to be, well, we can multiply by the other 2 cube roots of 1. So it's going to be 2e to the pi over 18i times e to the 2/3 pi I, which is 2e to the, what's that? It's going to be 12 over 18, isn't it? So 13 over 18 pi I. Z3 is going to be 2e to the pi over 18 I times e to the 4 over 3 pi I. So the three cube roots of 1 are 1, e to the 2/3 pi I, and e to the 4/3 pi I. The cube roots of the cube roots of 4 root 3 plus 4i are then this first solution here, and that first solution multiplied by the other two roots of 1. So this is 2e to the, what's this? This is, what are we going to do? Multiple. This is 24 over 18 pi I plus 1, so 25 over 18 pi I. But then we don't want the argument to go bigger than pi. So if we subtract 2 pi from this, we get 2e to the minus 11 over 18 pi I. Minus 11 over 18 pi I. Sorry, that's not enormously clear there, is it? The other way that you can think of this is that we've now got, if this is z cubed here, we've got something which is, this is length 8, we've got something length 2, and its angle is 1/3. So we've got one solution there, we've got another solution 2/3 of the way round the circle, a further solution another 2/3 of the way around the circle, and then if we continue around another 2/3, we're going to get our first solution back again. So that's using those nth roots of unity to find solutions to that equation there. We'll just go on now to look at how this can help us to solve a geometric problem. This one on here. So I think I briefly mentioned it. The nth roots of any complex number will lie at the vertices of a regular polygon, so with n sides, with its center at the origin. So we can use that sometimes to help us with geometric problems. So we've got this point here, the point root 3, 1 lies at one vertex of an equilateral triangle. We're going to find the coordinates of the other vertices and find the area of the triangle, and then we're going to look at a transformation of that as well. So if we represent P on the complex plane, P is well, on the complex plane it's root 3 plus I on the complex plane, or the Argand diagram, complex plane. And if we just sketch that very quickly, like this, we're going to have root 3 plus I there. So there's our P. Here's root 3 on the real axis. Here's I on the imaginary axis. So what's that equal to? Well, it's got a modulus of 2 and an argument of pi over 6. So it's 2e to the pi over 6i. So the other vertices of the triangle on the complex plane, so other vertices, well, we want to rotate by multiplying by the roots of 1, cube roots of 1 rather. So we often write the cube roots or the roots of unity as omega and powers of omega. So other vertices are, well, we've got 2e to the pi over 6i times omega. Looks like a W, Greek letter omega, and 2e to the pi over 6i omega squared, where omega is equal to, omega cubed is equal to 1, but excluding, not including omega is equal to 1. So omega not equal to 1. So arguments, so modulus still 2, and arguments we've got pi over 6 plus 2 over 3 pi over 6 plus 2 pi over 3, and pi over 6 plus 4 pi over 3. That's equal to 5 pi over 3. That's equal to, what's it going to be? That's going to be 8, 9 pi over 6, which is 3 over 2 pi. Normally we have our arguments going between pi and minus pi, so that's equivalent to minus pi over 2. So arguments 5 pi over 3, that's going to be rotating this around to here. Actually, let's just write down what that is. So that's equal to, so Q is, it's minus root 3 plus I, and R is minus 2I. So we've got this down here, minus 2I. That's R now, and then this one out here, what was it, minus root 3 plus I. There we go, Q. Minus root 3 plus I. There are the vertices of our equilateral triangle. This only works, of course, for regular polygons. So the fact that we know it's an equilateral triangle with its center at the origin allows us to do this. We were given these points in Cartesian form, so we should translate them back. So we're going to give them as minus root 3, 1, and 0, minus 2. Find the area of the triangle. Well, the area of the triangle is nice and easy to find now. We can say it's a half base times height. If you consider this the base, if you imagine it flipping it the other way up, its base, well, we've got going from minus root 3 to root 3, so that's 2 root 3. Area equals a half base times height. So that's a half times base is 2 root 3 times height is, well, that's plus 1 there, minus 2 there, so times 3. So it is 3 root 3 units squared. And then find the coordinates of P dash where we're rotating by pi over 6 radians anti-clockwise. So to rotate by pi over 6 anti-clockwise, we can just multiply each of our vertices in complex form by e to the minus pi over 6. So rotating by anti-clockwise, sorry, by e to the pi over 6. If you multiply, you're going to be going this way, that's anti-clockwise. So multiply vertices by e to the pi over 6i. Okay, that's the pi over 6 radians. So P dashed is 2e to the pi over 6 I times e to the pi over 6 I, which is 2e to the pi over 3i so we could write that as 2 times cos of pi over 3 plus I sine pi over 3, which is 1 plus I root 3. We're really just taking this p and we're translating it around another pi over 6. So this now becomes 1, this becomes root 3i. So 1 plus root 3i. If we do that to q dashed, well, this is going to rotate round by pi over 6, which is the angle that brings it to the negative real axis. So is minus 2. R dashed is, again, we're going to move that round by pi over 6. So this is going to be 1 minus I root 3. 1 minus I root 3. Or putting them in Cartesian form, this is going to be 1 root 3. This is going to be minus 2, 0. And this is going to be 1 minus root 3. So there's an example with an equilateral triangle. You might get a question which would ask you about the vertices of a square or a regular pentagon or a regular hexagon, and you would be able to approach it in the same way. You would just have, instead of the increasing arguments of 2 pi over 3 and 4 pi over 3, you would have a similar thing divided by whatever your power was. So for a square, it would be divided by 4, for a pentagon by 5, and for a hexagon by 6. Right, that's it for this section on complex numbers. You do need to do some practice of these geometric problems, but thank you for listening, and we'll leave it there for now.